let's study the special purpose counters. In this category, we have three special purpose counters. The first one is ring counter, the second one is Jhonson counter, or it is also called twisted ring counter, and the third one is up down counter. We start with the ring counter first. In a ring counter, we can design a 3-bit, 2-bit, or 4-bit. A 1 or a 0 is rotated in a ring manner, you can see here in the output. So for this, what we do, we connect the flip-flops. Here you can see I have taken JK flip-flops in cascade. Cascade means the output of the first will be the input of the next. You can see I'm joining them in cascade. In a cyclic fashion, the last one's output becomes the input of the first one. You can see the connection here. Next, join them in synchronous manner. That means the clock pulse of all flip-flops is common, and to rotate a 1 or a 0 in a ring fashion, suppose we want to rotate 1 in a ring fashion, what we will do, we will preset the first flip-flop by giving it 0 initially and clear the rest one by giving them 0 initially. So the output of the first flip-flop will be 1 of D, rest will be 0. So you have 1 here in the output, rest will be 0. For normal operation of flip-flops, preset and clear are given 1, and we will keep them at 1 for normal operation. This is at 1, this is at 0, this is at 0, this is at 1, this is at 0, this is at 1, this is at 0, this is at 1, this is at 0, and this is at 1 because it is connected to QA bar. After first clock pulse, these bits will shift to next flip-flops and your output will be 1 will move here, 0. So you will find with each clock pulse, the output will change like this. It will be 0001. The next time it is 010. You are seeing it here. We have given the first clock pulse. It has become 010 now. The 1 will rotate in the output in a ring fashion. If you want to rotate 0, then what we do, we preset other flip-flops. This will be made clear initially, then the 0 will rotate and your outputs will be like this. So you can design it in this manner too. A 0 is moving in a ring fashion here. Now, the next one is twisted ring counter, in which the flip-flops are connected. It is also called Jhonson counter. In the same manner, the way they are connected here, they will be synchronously connected. You will join the flip-flops in a cascade manner like this. The output of the first will be the inputs of the second. The output of the second will be the inputs of the third. The output of third will be the inputs of the fourth. And there is a change here. What is the change? Let's see. A twist is done here in case of Jhonson counter. How? The last QA bar are connected in a reverse manner here. JD is given now QA bar and KD is given now QA. So here there is a twist. That is why it is called twisted ring counter. In this case, we will clear all the flip-flops initially. You will not preset any flip-flop, you will clear all flip-flops. Your output will be this one in the beginning. Because there is a twist here, you will find when you will give clock pulses in these synchronously connected flip-flops, the ones will start storing in flip-flops on each clock pulse. So initially we cleared all flip-flops. When you give the first clock pulse, the 1 here will set this flip-flop and 0 will go here. So the order will reverse. Instead of resetting, the flip-flops start getting set at each pulse. So you can design even Jhonson counter for 3 bits, 2 bits as well as 4 bits. Now let's go to the third category, the up down counters. We know in all flip flops we have two types of outputs, Q and Q bar. We make use of this thing in up down counter. Let's study first up down ripple counter. QA, QB, QC here we make a 3-bit counter as a ripple counter, the design which we already know. To count up, we take outputs at QA, QB, QC. To count down, we will take outputs at QA bar, QB bar, QC bar. You can see if you are counting from triple zero, QA bar, QC bar, QB bar will be triple one. They will be reverse of each other. At 001, this is 110. So down counting happens at complements outputs. Now how to design it? The basic design remains the same. Here we have designed using JK flip-flops. We will take negative edge triggered JK flip-flops here because this is a ripple counter. I will make a signal, it is that will control, it will either give me up value or down value. If I will keep it at 1, my AND gates N1 and 2 will get activated. When I will keep it 0, AND gates N3 and 4 will get activated. The basic design was, in case of JK, when we designed the ripple counter using negative edge triggered JK flip-flops, we gave logic 1 to the inputs, to the both inputs. Here too we are giving in the same manner to all the flip-flops. You can see here. Now what is the purpose of these OR gates? You can see if I keep 1 here, these AND gates are basically activating the outputs QC, QB, QA if and only if this line goes 1. 1 into QC will be QC. Otherwise, if you keep it at 0, these outputs will become 0. Same here. Now, how up counting is done? I will keep this at 1. This is at 1. No, this is equal to QC. Now, the output of the AND gate is given through the OR gate to the clock. So, when you activate up counting, the output QC, QB, QA must be available. What we give up 1. My output QC is supplied here as well as here for the clock. Rest functioning is same as we studied in our normal ripple counters. Similarly, the down signal is connected through down bar. That means it will be activated when this signal is kept at 0. So my QC bar will travel to the outputs if and only if I keep that signal 0 and it is supplied as negative edge through the clock. And similarly, we can design up-down synchronous counter using normal JK flip-flops. The design is same, but here remember when we designed normal flip-flop, normal counters, the JK were kept at logic 1, the first one. The second one's inputs were, see them, that were the product of previous output and inputs, QC and logic 1. But here we are not giving logic 1, we are giving up down signal 1. That is the same thing because we will disable this counting by keeping it 0. But now here I will get QC. It is the same one, and I have given it not only taking output to the next flip flop through OR gate. Similarly, here you will see the next flip flops inputs are the product of previous one's output and input. Yes, it is connected to QB and its input because this QC was the input of the previous flip flop. Similarly, you will do the same connections on the other side where when you will keep this signal 0, up counting will not be performed, down counting will be performed as 1 is supplied here through the NOT gate and these gates get activated. Now the applications of counters. All counters are used not only to count the stages but they can be used as digital clock for there are many applications for auto parking controls, frequency dividers, or on lifts or on display